Hey folks, welcome back. Let's move on to the next topic in Multicast, which is going to be a PIM Sparse mode. We talked about PIM dense mode in the previous one, which was more of a where we flood the multicast traffic everywhere, right? And then we prune it, right? With the PIM Sparse mode, we don't forward the multicast traffic until someone requests it, right? So going back to our drawing board here. Right, so let's say we have an interesting topology here, right, which we'll be using. Now it brings a bit of, it brings a new problem, right? When we talk about sparse mode, it's all good that okay, you are forwarding traffic only when someone requests it, right? But what's the problem here? How does a router know where to find the source, of a multicast traffic, right? So you have a router probably here R3, right? How does this guy know where to find, S1? How does he get to know about S1, right? Or the source. In this case, this is the source, right? We are basically telling this guy has to request, but whom should he request and where can he find the source, right? Those are some actual questions. So to solve this, sparse mode brings the concept of rendezvous point. I hope I'm pronouncing it right? Or in simple terms, we can call it as RP. So rendezvous point, what does this bring to the table, right? With rendezvous point, what we do is we pick a router, obviously in our topology. Let's say in our case, we have picked R2 as my rendezvous point. And what we do is every router that receives multicast traffic from the source will forward it to the rendezvous point. So here R1 is receiving the traffic, it will forward to the rendezvous point. Each router that wants to receive the multicast traffic will also go to the rendezvous point. In this case, our R3 wants to receive because you have a H3 behind it. So this guy also will approach rendezvous point. And over here, say R4, even this guy will approach rendezvous point, right? So the whole traffic, the multicast traffic is sent right towards the rendezvous point, and then from there, right, all the routers who want to consume it, right, reach out and receive it from there, right? That's the idea about the rendezvous point. It's kind of like a meeting point, right? I think the meaning of rendezvous is a meeting point. So now, we solved a part of the problem by bringing in the rendezvous point. Now that brings another new problem, right? How does any of the router, so to reach rendezvous point, you should know who is rendezvous point, right? So how do you get to that? How do the routers in my network know who is the rendezvous point? Now there are two approaches for that, right? Either you can do it manually, right, wherein you can go and configure every single router, on every single router you can go and say R2 is the rendezvous point, right? That is one approach. Probably tiresome, but yeah, you can do that. Or there are dynamic approaches, right? And there are protocols such as auto RP, right, BSR and so on. We'll talk about this probably in some other video. But there are two approaches for doing it. In our topology, in our lab, we'll basically go with the manual approach, but we can do it with the dynamic approach as well. Okay? So now that being said, let's try to work out the, what will be the flow, right? What is the workflow of this particular protocol or the sparse mode? How, right from scratch, how it works, right? We talked about a couple of characteristics, but the most important part is how it all comes into play, how it all, makes a complete picture. So let's start with that. So let's assume for a minute that we've got our H3 over here, R3. So this is our source, right? At the moment, let's say, you have the traffic coming from here. Let's say there is some movie being played or some video being streamed, but no one in our network is interested. H3, H4, no one is interested in the traffic. So what happens first is very interesting. We have already configured R to be my rendezvous point. So what happens is that R1, as soon as he receives the traffic, right? So R1 will send the first multicast packet, right? Imagine I am doing a ping ICMP or something, right? Whatever is, you have a data packet coming here. So it will take the first packet, right? Whatever is the first data packet, it will take that and it will encapsulate it. It will encapsulate it into what we call as a PIM register packet. We will see this in the captures later. So the first packet is encapsulated in a PIM register packet and forwarded to my RP. Once the RP receives the PIM register packet, there are two options. Since no one is listening to this particular group, right? Let's say this particular multicast group is 239.1.1.1. Right now, no one in my network really is interested in this. So RP will reply back with a PIM stop, right? Or a reject. Basically, it will be a reject, right? So it's gonna say, please stop sending me. Right now, no one is interested, so it's gonna reject it, right, in this direction. Now consider another option. What if there were some users, or what if there were some multicast applications who are listening to it? Then it would accept the register packet, right? So those are two interesting things, right? So it's basically going to reject it by sending a PIM register stop packet, and that's the end of it. Is it? No, that's not the end of it. So what's going to happen? The R1 is going to remain quiet for some time. It's going to start a counter or a clock, right? It's going to start a counter, and it is going to remain quiet for by default it's going to remain quiet for like 60 seconds. When the timer expires, this R1 is a very enthusiastic kid, right? So when the timer expires, it's going to come back. It's going to come back again with another PIM register message or packet. But this time it is not going to encapsulate the data packet, which was from here, right? Whatever. It's going to directly send a, it's basically called as a PIM register null packet, actually, because it's not encapsulated, doesn't carry any kind of encapsulated data. It's just a packet which is formed by R1 and sent down, right? It's just a simple request to ask RP if he is interested now, right? Just to check on him, just to check, hey RP, are you interested now? Do you want me to forward you the data packets, right? So it's going to do that. So this will continue 60 seconds. Every 60 seconds it's going to send a PIM register, and if this guy is not interested, it's going to reply back with the PIM register stop. All right, so we have set the context. What is happening when we don't have data, right? I mean, we have data flowing in, but we don't have anyone interested. Awesome. Now let's bring in the concept of, let's say, what if someone is interested, right? So let's say we've got our or let's take probably the other guy on the top. Maybe that guy makes sense, easier to explain. So let me take this guy, H4, right? So the H4 is now interested. So what is the first step? Whenever a client is interested, the first step is they're going to send a IGMP packet, IGMP join, right? Excuse me. So IGMP join is nothing but a membership report, right, which we have talked about in the IGMP video, right? The IGMP join is nothing but your membership report, which is sent towards R4. R4 will look at this and is gonna say that, okay, I've received a membership report for what? For the group 239.1.1.1, and he will right now create what we call as a PIM join packet. Right, a PIM join packet, but where? Towards the RP. Everything happens towards the RP, nothing happens towards the source, right? So it's going to send a PIM join packet, right? But before that, so as soon as he gets the IGMP join, first thing is R4 will try to figure out how to reach RP, and what it is going to use, obviously, the unicast routing table. Right, so in the unicast routing table, it will know that, okay, to reach RP, it has to use this interface, which is Ethernet 0/2, right? And that's the reason it will send the PIM join along this interface. Now R2 receives the PIM join, and he understands that, okay, someone is interested, right? And he is going to send the PIM join in this direction, right? So basically, that's how the PIM join is going to come in either one of the cases. Either you're connected directly to the multicast client, right? So in which case you received a IGMP join, and that's why you will send a PIM join, or you send a PIM join because your downstream router, in this case R4, has sent a PIM join towards you. So you go and check your routing table and send a PIM join towards your RP. In this case, the source is here, so it's going to send a PIM join towards R1, We'll see that workflow later in the captures, right? Actually, it's not going to obviously send it immediately, this one, because let me just get rid of that, otherwise it's going to cause confusion. So the PIM joins are sent towards the RP, right? So now R2 basically knows that someone is interested. Now the next time this guy, the R1, the enthusiastic kid, when he comes back saying, hey, are you interested in, it's going to send a PIM register, right? So when it sends the PIM register in this direction, this time our RP will not block it, or it will not send a reject, right? It will not reject the PIM register. And as a result, R1 gets to know that, okay, looks like RP has found some candidate who is interested in my traffic, right? And that's where, what we call as a root path tree is formed, right? In the previous video, we talked about SPT, didn't we? Shortest path tree. But this time, in a sparse mode scenario, what we create is a root path tree. It's also called as shared distribution tree, right? Tree, very similar to what we had in the previous one, right? Here we are basically creating a root path tree, right? So the concept of joining the RP is basically called as a root path tree, and in this case the RP is the root. In my previous case, who was the root? The source was the root, because it was a source tree. But now we are talking about root path tree, and the RP is the root, right? Because it decides where to forward the multicast traffic to. So each multicast group will have different sources and receivers. So we might have different RPTs in our network, right? If we are having only one group, right, and one source, probably it's going to be just one RPT. But if you have multiple sources and multiple receivers and obviously multiple groups, then you're going to have multiple RPTs in your network. Cool. So what we have created till now, let me just clear this and let's see what we have achieved, because we are still not done. This is where it gets really fun, right? So what we did was we created a root path tree. Let's draw the root path tree. So we created a root path tree from here towards RP, this guy, like this, right? Forget about H3 for now. Let's assume that only H4 is interested. So this would be the root path tree which would have been created. We'll look at this, how it looks up in the show commands as well. Now root path tree has been created and the traffic starts flowing along this nice tree which got created, right? The traffic is flowing, it's being sent to RP, and from RP it is going here. But don't you think something is off here, right? Don't you think it is very easier for the traffic to just go in 2 hops instead of going 1 extra hop here, right? How about I have traffic coming from here, R1, instead of going to R2 and then going to R4, why can't I go to R4 directly, right? I'll be basically reducing the latency and improving, right? That will be more optimal. Now that's exactly what will happen. So right, so that's exactly what's going to happen. So we are now entering towards making our multicast more optimal, right? So right now, as soon as initially when the traffic starts flowing, it will be the root path tree, which is this one, what we have right now. But then, right, once my R4 receives the traffic, once he is receiving the traffic, let's say this source is, I don't know, 192.168.1. Let's say 1.1, right, is the source. So once our R4 receives that packet, he's gonna decide, okay, my source is 192.168.1.1, then why should I simply waste my energy traveling this extra mile and going like this, right? In my routing table, I have a path to reach 192.168.1.1. It's direct path. Why should I go in a roundabout way, right? So the intelligent R4 is now gonna start sending PIM join along this interface. Which one? Along this one. It's gonna say, hey R1, I would like to send a PIM join, right, along this interface, because I want you to make this interface forwarding, right, and that way I can reach the source very easily within the 2 hops instead of adding an extra hop and going like this through R2. Right, so it's going to send the PIM join. Once R4 receives it, right, he realizes, and so once the path is formed, so as soon as this happens, a new path is formed. So that path is your SPT, right, which we have done in the previous video. SPT, source shared path tree, or source shortest path tree. Okay, I get confused sometimes. It is, or in short, you can say it's shortest tree as well. Right? So once that is done, let me just clear everything now. What's going to happen? The root tree or RPT will no longer be used. Rather, R4 will directly talk to along this path, right? And it will not do the whole roundabout, and it won't use the RPT anymore, right? Because this is optimal, right? Yeah, so that's where the flow ends, right? Isn't that fun, right? So we started with looking at what happens when there is no traffic, right? The whole the whole concept of everyone coming and joining the RPs and forming the root path trees and all of that. And then once the traffic starts flowing, right? Once the traffic starts flowing, in fact, once the users start to, or once the clients start to enter the network, right? Once they send a IGMP join, then their PIM joins created, right? And a root path tree is created. And once the root path tree is there, the traffic starts flowing. But then, a downstream router, right, is going to think, okay, why can't I reach my source directly? Why should I, use a non-optimal path? And that's where the RPT is going to kind of like transition, right, to your SPT, right? So we'll see all of that happening in our lab, right? So let's get rid of this and let's go to my lab. All right. So I hope that's good. So I have my lab here. All right, looks good. So the IP addressing scheme is pretty simple. This is 192.168.1.0. This is R1 and R4, so it will be 14. This will be, I think, 24 maybe. I think this will be 12. This will be 23. So it's very straightforward. You'll get to know as I go about configuring this. Okay. So starting, what's the first step? Let's go and enable multicast routing on all the routers. On T, let's do on R1. So R1, and then we have got 2. Let's do R3 and R4. Awesome. Then, so where are we? We are on R1, right, over here. All right, so what we'll do is first let's go and enable we'll enable our sparse mode, right, on one of the interface. Let's do it on probably the Ethernet 0/1, right? Let's go to R1, as I want to show you the packets, right? So that's why I'm just going to enable on only one for now, and we're going to say IP PIM Sparse mode. Hope I have my captures in place. Yeah, I have my captures. So let's do this. So let's do IP PIM Sparse mode. And as soon as I do that, I think this one is the, let's do a PIM here. There you go. So I have the PIM hello packets, right, being sent. You can see here on the right side, it's a hello packet being sent with some bunch of, hold time is there and all of that. 105 is the default hold time. Now let's take that to the next level by enabling the same thing on where 12 dot, okay, they are changed for neighbors, this. Okay, cool. So let's go and do the same thing on which interface? On R2 as well. So R2 as well. So it's going to be interface Ethernet 0/1. Sorry. Let's do IP PIM sparse mode. There you go. So I enabled it on that, and there you go. We should get this log. This log says the PIM neighborship has come up between R1 and R2. Right, now let's do it in bulk. We basically need to enable it on all the interfaces, on all the router interfaces. Right, so let's do that. Right, so on R1, let's go back and enable it on the rest of the two interfaces where we want. That's 00 and 03. Right, so that completes R1. On R2, we want it on 00 and 02. Let's do that. Go to R2 and there you go. That's done. On R3, we want it on 00 and 03, right? Those are the two interfaces. So fix those, and I think that's good. And the last guy, which is R4, which is 00, 02, and 03. Alright, so that's R4 and alright, so that's good. So we can see the PIM neighborships are coming up as and when we do it. Alright, so next, let's check our, before that, let me check if I have my OSPF. Just want to make sure that OSPF is running. I think I don't have OSPF, do I? Run section router. Damn it, so I don't have my OSPF, so I'll have to put my OSPF. Let's put the OSPF. So let's quickly check the addressing scheme. Yep, 14, 12, and good. So on R1, it's going to be 192.168.1.0. Then we gotta have 14, and then we need to have, I believe it is 12. Right, so let's do this. So let's go and put the OSPF part here. There you go. Same thing on R2. It's gonna be 12. I believe 23, and let's check this. To show IP interface brief. So it is 12 and 24. Right. To 12, 24, and 23. 12, 24, and 23. Yep, that looks good. So let's do that. Alright, so R2 is good. R3, we will need just 3 and what is this? This is 23. Right, so we'll just need 3 and 23. Let's do that. So that's your R3. And the last guy, which is R4, which is 4 and so let's put 4. We would need 24. Is it 24 on R4? Let's check. Do show IP interface brief. Yep, that's 24. So, and we will also need 14. Did I get that right? So we basically need 4 here. We need between 2 and 4 we need 24, and we need 14 down here. So let's do that. Hope that's correct. Yeah, there you go. So we've got all my OSPF up. So let's check. Let's check. Do we have do show IP route? Yep, looks like we have the 3.0, we have the 4.0, which is fine, which is perfect. That's exactly what I want. Perfect. Next, so let's move on and let's now get into, let's quickly check if my PIM neighbors are all good. So let's do show. There you go, my PIM neighbors are good. Here on this guy, let's check. Yep, I have 3 PIM neighbors here. And what about this one? I have just 1. That's fine. On my R4, we gotta have 2 more. Yep, that's perfect. Yeah, that's good. So the PIM is all good. Nothing strange over there. We have done this before. Now let's check the multicast routes. We have enabled sparse mode, right? So let's go to R1 and let's see. If I do show IP mroute, what do we see? We are seeing this 224.0.1.40. This is mainly because of the auto RP. I think I covered this in the previous video as well, but this multicast group address is actually for auto RP discovery, right? So if you're using the auto RP feature, then you can basically use this particular group to kind of advertise to the rest of the network as to who the RP is, right? But in this particular video, I believe we will not do the dynamic learning of RP, rather we want to do the static, right? So what we do is, let's go and disable auto RP, right, on all of them, because we want to do the static way, right? So there you go, no IP PIM auto RP on this R2 as well, R3 and R4, right? So we have disabled auto RP everywhere, right? So probably might take some time for it to go away. Probably will take some time to go away, but anyway, we have disabled auto RP everywhere. And now we will go about configuring the rendezvous point, right? We'll manually configure the rendezvous point. In our case, we want to put the rendezvous point where? On R2 here. So what I'll do is, let's first create a loopback, right? It's always good to create a rendezvous point and loopback because physical interface might go down, right? So the loopback is something like 2.2.2, right? That's the IP on my loopback. And remember, I have a OSPF here. Let me just advertise this guy inside my OSPF as well. Awesome, that's done. Now we have created the rendezvous point on R2, but we have to manually go to every other router and tell who the rendezvous point is. So we go to R1, we tell R1, we tell R3, and we tell R4 as well. We are basically telling them, guys, this is your RP. This is the person whom you have to reach out to, right? Awesome. So now when we do that, you should have a tunnel come up, right? So everywhere you have the tunnels come up. On R1 you will have one tunnel, on R3 as well one tunnel, and R4 also you have like one tunnel coming up here, you can see. But on R2 we should actually have a couple of tunnels coming up. Let's see what has happened. Show IP interface brief. Let's give it a minute. Maybe let's I think it probably will not appear there, so let's check here. So IP tunnels, IP PIM tunnel. Okay, so it's not an up. Let's give it for a few seconds. Oh, I think I missed out on putting the RP address on my R2, right? That's why probably. Let's do that. So there we go. Now if I, okay, so I think it's there, I can see that, but let's see, do we have the tunnels? Okay, sorry, I put this on R1 again. Let's put this on R2. I think I missed on putting it on R2. Right, so you gotta put the RP everywhere, right? See, now you can see both the tunnels come up. Cool, that's exactly what I wanted. So you have to put the RP address on all the routers manually, right? Okay, so let's go and check the tunnels. So we should have some tunnels come up now, right? So let's look at those tunnels. So let's go to R1, and there you go, we have one tunnel up, right? Which is the first tunnel interface is actually kind of like use it for encapsulating the first packet, right, in the PIM register message and forwarding it to the RP. So this particular tunnel will be used for that, right? So all the non-RP routers will have just one tunnel. You can check that out. Even on R3 we are going to have, let me just clear the screen a bit and let me run that command again. There you go, we have one tunnel. Let me clear the screen. Another. Awesome, there you go, one tunnels. But you go to R2, we'll see two tunnels, right? One is your encap, another one is your decap tunnel, right? The RP is going to obviously have an additional tunnel which is used for decapsulation of the PIM register packet, because only this guy is going to get the PIM register packet thrown towards him, right? No one else is going to get. So that's why he's going to have a decap tunnel as well to decapsulate that PIM register packet, which I talked about in my earlier lecture. Alright, so now let's go and check out this PIM register packet. The first packet, right, in my sparse mode is the PIM register. So let's go and enable debugs everywhere. Debugs, debug here as well, and here. Okay, so done. Debug is on, and let's start some source. Where is our source? We have our S1 here, which is our server, right? Let's create some traffic. Let's generate some traffic. PIM 239.1.1.1 repeat 1000. So we have generated some traffic. Let's go on R1. What do we see? On R1 you can see, so the traffic is coming like this. So we can see some logs or some debugs here, right? So R1 will basically encapsulate, like I said, the first multicast packet. In our case, it is nothing but ICMP is the data. So it will multicast. It will create this PIM register packet towards my RP, and we'll check that. Should probably have got that one here. PIM. Okay, here. I think this is the one. Right, so you can see here, this is the first PIM register packet. That's why it has encapsulated, which means the data, it has taken one packet, the data packet, and it has encapsulated it. Right, this is the packet towards my RP. And see here immediately, our RP replied back with a register stop. He's telling, don't send me any more packets because I don't have anyone to send it to. No one is interested in this particular source right now. No one is interested in this particular group right now. So you can see this guy has sent a register stop towards your R1. Alright, cool. Now that, like I said, there will be a sub timer which is going to be started as soon as he gets the register stop. Right, he is going to start that timer. He has sent sorry, not this one, this guy. So there will be a timer. I think that message is not shown here, but there will be a timer which is going to be started. Right, 60 seconds, and for 60 seconds it's going to remain silent. Okay. Now let's go and enable debugs for PIM as well. Right, what debugs did I enable here above? Did I do it for? Okay, I've enabled PIM itself, right? Just make sure that I've enabled it. So on R1, R2, and also want it on R3. Okay, now it's already enabled. Cool. So now what we'll do is we'll go to my H3, clear the screen, and let's go to H3. Where is H3? Here. And let's say this guy wants to join, right? Ethernet 0/0. See, right now the pings are not being successful because obviously there is no one to receive this particular stream, right? There is no one interested in this data. Now we have our H3, right? And we'll go inside the interface and we'll say IP IGMP join group and 239. Okay, which group was I sending over here? I was sending it to 230. Okay, so let me just stop this and let's go to this guy 239.3.3.3. I'm gonna join. As soon as I hit this join, we'll see some cool debugs coming on my R3. So let's see that. There we go. On R3 I have some debugs. Right, so it's going to check with RP, check 2.2.2 into the entry, right? So star comma G entry, which tells us that we are joining the we are joining the RPT, right? The root path tree, right? So this is the root path tree, and the G is basically the source. The multicast group address 239.3.3.3. And I don't think I have captured this packet, so I can't show you the PIM join here, but basically a PIM join would have been sent. See here, there is a PIM join which was sent towards R3, has sent the PIM join towards R2. Right, and so because R2 is the rendezvous point here, right? Cool. and on R2 we'll basically have the same logs saying that we have received a PIM join, right, and it will take this interface Ethernet 0/0 and it will put it in the forwarding state, right. We should have that as well. Look here, Ethernet 0/0 has been put in the forwarding state. Perfect, that's exactly what we want. Because why it is putting this interface in forwarding state? Because now from now on, if it is getting any traffic for this group, it can forward it. Let's check on R2 for this particular multicast group. What do we see? Right, so this is your root path tree, RPT. Right, you can see the RP 2.2.2 mentioned here. Right, the S flag here mentions, it means that we are using the PIM Sparse mode. Nobody is currently sending traffic to this group at the moment, so the incoming interface is kind of like null. The outgoing interface is in the forwarding state. Same thing, we can also see the same command on R3 as well. There you go. On R3, what do we see? We have an interesting flag called SJC. S stands for sparse mode. J means this is the SPT bit, right? So we are basically saying that when possible, right, if possible, R3 is ready to switch from RPT to SPT, right, from root path tree to the source tree, which we talked about, right, when possible. Right now, no. Right now it is in the root path tree because there is no traffic at all. The SPT has not even been created. C basically means that I have a directly connected multicast member connected directly to me. Now we'll see what fun happens when we go and actually create traffic. So let's go back to my server and create traffic for this particular group. So what do we see? Let's wait for the reply to come. Probably on R1 we should start seeing some cool stuff. There you go. I think we are seeing some good stuff on R1. Is our receiver replying? Yeah, there you see our receiver is replying. So from here you have generated the traffic and our H3 is replying from here. You can see the reply going in here. Right, so R1 has received the PIM join. Right over here, received the PIM join on Ethernet 0/1. So because it obviously sent a register as well. See, PIM register was sent towards R2 this time, but this time there was no PIM register reject sent in the opposite direction, because R2 knows that it wants the traffic. It has someone interested in the traffic, so it is not going to kind of like send a register stop, right? So it's going to accept. So it wants really. So we could probably see that here as well. This one is probably for the previous one, right? Because you can see right after that there is a join which has gone in, right? And this time it is actually joining, right? So you can see the join has gone in from RP, right, for this particular group. Sorry, not this one. This is 224. Yeah, this is correct. So it wants to join this 239.3.3.3, right? So because of that, this particular interface becomes forwarding now, which is RP towards my R1. That particular interface becomes forwarding. There'll be a bunch of logs created even on my R2, right? But mainly the main idea here is, now if you go back and check the same output as before, we'll see some cool stuff. There you see. Let's just run that again, but this is something which I really want to show you guys. What has happened is, right, what has happened basically is that we have this particular or R2 has actually joined SPT, right? This was the RPT, right, the root path tree, but now you see R2 has joined the SPT over here. Excuse me. So how do you know that? So you can see the T flag, right? As soon as you see the T flag, it should give you the hint. The T flag basically stands for that. You can see here SPT bit has been set, which means it has joined SPT. So for this particular source 192.168.1.1, it has joined SPT. So SPT has formed from 192.168. So in this case, the interesting thing is, because you have your R3 behind your undo point, right? The only possible path is like this. So the SPT and the RPT is going to be the same, the tree is going to look the same because there's only one possible way, right? It's going to come like this, and because all of these are equal cost paths, this is the only way, right? So, but the main observation here is that, R2 has actually joined, not just R2, R3 also would have joined or switched from where? From your RPT to SPT. So you can see that here. There you go. See, we have created an entry. So this is your SPT, and you can see the flag T. Right? So that makes sense. What else? The only thing is, technically speaking, the SPT needs more memory, right? Because earlier you just had one entry. Now you have one more entry. Imagine you have a big multicast network with multiple sources, multiple groups. It's obviously going to consume a lot of memory, doesn't it? So in that case, you also have a mechanism for not switching to SPT, right? And within one small command, you can make that happen, right? So you can run a command on my R3 saying that, sorry, not that, IP PIM, I think it's IP PIM threshold, SPT threshold, I guess. SPT threshold, you can put any threshold, but I'm going to put like infinity, right? So, so we are basically, kind of like preventing the switchover from happening, right? So what we did is, what this command does is, by default, actually, the router is going to switch to SPT, right, whenever the traffic exceeds 0 kilobits per second, which means immediately, right? As soon as you get the traffic, the router is going to figure out, okay, the source address, and then it is going to create its own source path tree like we explained earlier. But what we are telling now is, basically do that switch when the traffic reaches infinity, which is obviously never. So, you are basically kind of like tricking the router into never switch into SPT, right? So now if you probably, it's going to take some time. I'm not sure if that would have happened already. It will take some time, but after some time, after the expiry of this particular counter, we should basically be seeing only this one single, entry. We'll not see the second entry, which is the SPT would have disappeared, right? So we still have like 2 minutes 28 seconds on that. So we'll come back to this probably at the end, and we'll check this entry again. Now we'll do something interesting on the top side. We have a H4. We have one more router here, right? So here it will be very evident, because initially it will join the root path tree by going to the RP and then going like this. But after that, like I explained, it will no longer go to the RP, rather it will go straight. So it will be very much evident here rather here, because in this case R3 was behind the RP. So, via the RP itself was the only possible path, right? But in H4 it's going to be different. So let's go and do that. So let's go to H4 interface 0/0, and we'll go and join probably, what was I creating here? Okay, so let's stop this probably. Okay, let's give it a second. I think this has to complete. Yeah, okay, that's weird. Okay, so it stopped, which is good. So let's go to H4 and we'll join 239.4.4.4, and on my S1 I'll basically go and create a new stream which is for 239.4.4.4, right? So we should start getting replies for this guy from where? From my H4, because this guy has joined, right, this particular group. So there you go, we are getting the replies from him, and this will be fun to watch. So here on R4, there is R4. Yeah, so on R4 we should see it has already sent the prune, right? It has already sent the prune towards R2, right? Because it has already joined the SPT here. Look, it has already joined the SPT, and as a result, right, it has already sent the prune. So we can also see that information on R2. So on R2 we can see that because for this particular entry, right, for 239, you can see the outgoing interface is null, right? So R2 is literally not getting any traffic, right, for this particular for the new stream which we just now created. Because why? Because R4 has transitioned from root path tree to your source tree, because that is the most optimal way to reach the source, right, and not go in a roundabout way via the R2, right? So let's now go and check if this has completed. I don't know. Nope. Okay, still there is few minutes on that, but anyway, so once, like I said, once the timer expires, we should see that happening. Anyway, so that's mainly what I wanted to show you guys in this one, right? So just to summarize, your PIM Sparse mode, right, it uses your rendezvous point as like a central point for your multicast traffic. Routers will use your PIM register packets, to kind of register sources with the rendezvous point. We saw the register packets, how they were created. The first packet is always encapsulated, but the subsequent packets are all null packets, right? We could probably see that here. Okay, we could like pick one of these guy. You can see here, not this one, because that was for the new stream. See, these are your subsequent null packets, right? And okay, wait. So this was your IPv4, yeah. So you can see here, it doesn't have any ICMP in it, right? These are all your subsequent, registered packets. They are all null packets. The first packet is first register packet is the one which will contain data, right? It will encapsulate data and it will send, but the subsequent ones are all null packets. The router that sends the PIM register will start a suppression timer like a 60 seconds and will send a PIM register null packet every 60 seconds. Routers with receivers will join the RPT first, that is a root path tree for every group, right, that they want to receive, and the RPT is basically nothing but the star comma G, whatever you see, right? That's your RPT. We saw that on my R3 as well over here. This is your RPT. And once the routers with receivers get the multicast packet from the RP, they will switch from RPT to your SPT. And then we have also a mechanism to prevent that switch from happening. I showed you a trick on how to do that, right? Thanks for watching, guys. Hope that was useful. Bye.